First of all, this is basically the outline. I will start introducing the general concept of the what, why, and how of model sharing, and then moving to present this concept of a model as a resource paradigm for sharing models in the concept of model web, and then some more details about the potential design of a MAR framework for open model sharing. So the first point is that I would like to delimit our domain of discourse to the scientific models. Actually, we don't have any, let's say, agreed definition of what a model is, but in the last decades, there was a general agreement on one essential characteristics of model, which is called surrogative reasoning. Surrogative reasoning means that we use one thing, which is the model, as a surrogate in thinking about another thing, which is the target system. So basically, we can define our scientific models as any kind of epistemic artifact, which means something that we build for knowledge, which supports this surrogative reasoning. And this actually leaves a lot of space for many different kinds of scientific models. We may have strictly representational models like simulation models, or non-strictly representational models like models that actually represent alternate realities. We may have mechanical or mathematical or computational models. We have analog or digital models. We have physics-driven and data-driven models, and Stefano mentioned in particular these machine learning, deep learning models and their importance today. But of course, for the digital earth, which is our domain of interest, we will specifically focus on those models which have a digital representation and that are computable. So the next point is why do we really need to share these digital and computational models? Generally speaking, there are two main reasons. One is actually internal to the scientific practice, for example, for validating models by the scientific community, or for documenting the scientific knowledge generation process, or for intercomparison of models, or in general for reusing them in similar or different contexts, for example, for testing hypotheses. The second general usage is for science-based decision-making, for example, for making a decision transparent, also, for example, for decision makers' accountability, and also for using in integrated modeling. And these are typical uses that are part of the vision of open science and open knowledge, which are often considered as synonyms, but it's useful actually to restrict open science to the openness of the scientific practice and open knowledge to the openness of knowledge generation and use also beside and beyond the scientific practice. But at a high level, the requirements of open science and open knowledge are similar, and we can summarize them in 4 high-level requirements. One is transparency, which means the possibility to have a full documentation of the knowledge generation process. Then we have the requirement of reproducibility, which is the possibility to repeat a scientific experiment. Then replicability, which is the possibility to repeat an experiment, but changing some elements, for example, input data for a model. And the last and the main, let's say the more general, is reusability, which means the possibility to reuse a knowledge generation process in a more general context, including, for example, integrated modeling. And this last requirement is particularly important for many reasons. One is that science today is typically multidisciplinary and interdisciplinary, so requiring to put together models from different disciplines, but also in general for addressing the global challenges that we are facing that are themselves multidisciplinary in nature. And in such direction, in 2007, Gary Geller and William Turner introduced the concept of model web in the ecological domain in particular, as a dynamic network of computer models that together can answer more questions than the individual models operating alone. This was actually taken over by the Group on Earth Observation, which launched a GeoModel Web initiative led by Stefano and Gary Geller to actually design and build a dynamic modeling infrastructure called the Model Web to serve researchers, managers, policymakers, and the general public. And here I put the DOI of a paper that we wrote with Gary Geller on the Model Web initiative. So, how to share models? Stefano already introduced this. Actually, as of today, let's say model sharing is generally achieved in two ways. The first one is basically providing a tool with its own data, its own models, and graphical user interface. And there are many examples of these kind of tools in virtual research environment, in virtual laboratories. And it is also the approach basically of adopted more recently with the data cubes. These tools have big advantages in the sense that they are often tailored to specific user categories, and for them they are typically really user-friendly. They can support the transparency, of course, documenting the process, and of course, reproducibility, which is repeating the same experiment. But they have some limitations in terms of replicability because, for example, just adding new input data can be a complex action requiring ingestion of data, so making this quite difficult and complex action. And limitation on the reusability because typically the model is embedded in the tool. The second approach is the providing of model with the capability of running it through a networked interface, which allows to send parameters and input data, so solving the problem of replicability. But also this approach has limitation on reusability, because as Stefano said before, actually it's the provider who decides the capabilities of the services, for example, how much computational power to dedicate. They decide whether there is some limitation, for example, on input data size and so on. So basically, this approach that we can call model as a tool and model as a service fit well for running models, but actually models need something more that to support, because there are many other kind of scenarios where a model can be useful. For example, we may need to inspect model, to compare them, to move to another infrastructure, and so on. And so actually, we should consider a model as a more general resource than just something to run. And this actually links to the very difference between services and resource. A service is defined as a work done for others, while a resource is defined as something that can be used to help, which has some value for users. So a service is basically an action, while a resource is a thing. And this means that the provider decides actually what to offer as a service, while the user decides how to use a resource, which means that services are more provider-driven, while resources are more user-driven. And this has actually a clear parallel in software architectures, where we have two of the major architectural styles, which are indeed called service-oriented architectures and resource-oriented architectures. In service-oriented architectures, the application is decomposed in distinct units of logic, can be very complex or even very light, like microservices, and these are exposed to other machines. And of course, since they can be very different, they must have dedicated interfaces. And for that, they also require some ancillary services, like, for example, a registry of the available services and with the description of the different interfaces. On the contrary, resource-oriented architectures are based on a general concept of resource, which is often defined as an item of the information space. And since all the core elements in a resource-oriented architecture are pieces of information, we can have a uniform interface providing the basic set of actions for these pieces of information, like the possibility to create them, to retrieve, update, and delete them. And of course, we have a drawback, which is that the complex actions must be created with a workflow of basic actions. And so it seems in general that SOAs, so service-oriented architecture, are more intuitive. And the question is if a resource-oriented architecture can be built as a flexible, extensible, and robust infrastructure. But the answer is yes, actually, because we have an example of big and very flexible infrastructure, which is based on a resource-oriented architectural style, which is the World Wide Web, because the web is based on a resource-oriented style called representational state transfer. As all the architectural styles, REST is defined through a set of constraints, which actually guarantee some specific properties. And in particular, REST defines some specific constraints. One is that interactions are stateless, which means that when you request a resource, what you get is not dependent on previous requests. Of course, in REST, we have a uniform interface, and one particular aspect is that since interactions are stateless, to build applications, it introduces this concept of hypermedia as the engine of application state, which basically means that an application is built navigating the resources through the navigation links that are present in the hypermedia representing the resource. So the question is if we can imagine to build a model as a resource framework based on the same architectural style of the web. To do this, we need, starting from the open knowledge requirements, to first identify the logical resources needed for this MAR framework, and then to design the functional components that interacts according to the REST constraints. The first point, so the identification of resources, is the most complex one, because in resource-oriented architecture, of course, resources are the core concept. And we started actually from the model web conceptual view, and we refined it, building this conceptual view, which is, of course, centered on the core concept of model. And for us, the model resource is the algorithm that computationally describes the overall general model. And this is important because algorithm is an intermediate concept between the high-level semantics of the model, which means what kind of output it produces, and the low-level implementation code. And this is reflected in our conceptual view when above the model we have the model description resource, which include all the constraints, including the semantics required for input data and output data. And below the model, we have the model implementation resource, which includes the different implementing codes. And then we have a model run resource, which actually is related to the model implementation, but also with the realization of input and output datasets. So these are basically the core resources that we identified. In terms of logical components, actually in resource-oriented architecture, this is easier because actually we need components respecting the constraints. And for REST, this means that we need clients that are able to access resources through a uniform stateless interface, that are able to visualize and navigate hypermedia and to run mobile code. So basically, one example of this is browsers and the possibility to navigate through typical web resources. So how is it possible to build applications? One easy example is, for example, for reproducibility requirement. Generally, one application could be built with a sort of engine to discover existing models, to get an inventory, and through the inventory moving, for example, to a description of a model. The different kinds of description could be the source code, or could be, for example, a web form for running the model. It could be, for example, a predefined scenario for reproducibility, or even the possibility to select input data for more general replicability use cases, and then getting the output. We can imagine many different links allowing to navigate forward and backward among the different resource representation. But this is something that actually could be also developed with model as a tool and model as a service approach. So the real advantage of model as a resource approach is when we consider that one important resource and representation is the source code. For example, in this approach, we could be linked to a repository of code. It could be, for example, one GitHub or GitLab repository, where we can actually get the code and we can download it. We can build a container which can be sent to a cloud platform to get a result. And what is the problem actually? Is that this last set of action, like the user builds the model, prepares a Docker container, moves it on a cloud platform and runs it, is very complex action. And it is well beyond the typical capabilities of end user. But when we have complex action, what we can do is to provide this as a service. So it seems that we are developing a model as a resource framework and find that we need a service, which seems strange, but this is actually possible. We can actually introduce services in an architecture. Of course, since architectural styles are defined by constraints that guarantee the system properties, we cannot simply mix styles because this could bring us to violate constraints. For example, a service has typically a dedicated interface which does not map with a uniform interface of REST or generally resource-oriented architecture. But what we can do is to adopt different styles in different subsystems and make them dialogue through gateways, which expose resources on one side and call services on the other side. And so this is actually the simplified view of our design of the MAR framework, with a RESTful subsystem for interaction with resources through web servers and gateways, and where applications are built through hypermedia navigation, and a service-oriented subsystem with unconstrained interfaces and gateways to expose services through resources. We also identified some of the services which will be necessary to facilitate the end users, and of course, some of them are actually services for building and running models. And in the next presentation, Mattia will talk specifically of some prototypes that we developed. I would like to conclude my presentation with some thoughts, some reflections about points of strength and weaknesses of this approach. In terms of strength, main strength is the separation of concerns, which means that actually every user enters the system at their level of expertise and concerns. For example, end users interact with the system through a common web client. Application developers can develop applications as web apps. Service providers are free to develop their services freely, just providing web interfaces through gateways. And finally, resource providers can use their own preferred technologies. The system is generally extensible and viable because it's based on two well-known and well-adopted architectural styles. The main weakness is that it is based on a multi-style architecture, and multi-style architectures are fragile, which means that they need some governance because we must be sure that this architecture is an invariant. There is not any violation of this architectural style, actually. And also, it is necessary to provide some facilitating services to make it work and to reach a critical mass of users and providers. And I conclude my presentation, thanking all of you for your attention and leaving you with the DOI of the paper that was actually published just yesterday, where you can find the details of our work on this model as a resource paradigm.